Hello, in this video we'll be working through Unit 7 homework problems 31 through 41. For 31 we want to find the volume of the solid of revolution formed by rotating the region bounded by the x-axis and the graph of y equals fifth root of x from x equals 0 to x equals 1 about the x-axis. Let's start by sketching a graph. So the fifth root of x is something like this. So this is our y equals the fifth root of x, and we want the region from 0 to 1. So we'll put 1 right about there. And we are rotating around the x-axis. We're going to use disk method here, so we want to draw our reference rectangle perpendicular to our axis of rotation. That makes this a dx problem. Okay, so here's our shaded region that we are rotating around the x-axis. So our setup, since this is a dx problem, is going to be the integral with respect to x. And then here we want x values for our lower and upper limits of integration. We're going to integrate from x equals 0 to x equals 1. The dx is the width of the rectangle. Remember, an integral is just a special Riemann sum. So we're summing the areas of a bunch of rectangles. We want the width of the rectangle, which is dx, times the height of the rectangle. And this vertical height we can get by doing top minus bottom. So fifth root of x minus 0. Now, if this was the integral I calculated, all this would give me would be the area of the shaded region. But we want volume, so we're going to do volume equals pi times this radius squared. And that's going to equal the pi times the integral from 0 to 1. The fifth root of x squared is the same as x to the power 2/5. And we can evaluate this using our power rule. The integral for x to the 2/5 times dx is x to the 7/5 divided by 7/5, which is the same as multiplying by 5/7. And we're evaluating from 0 to 1. So we sub in the 1 and we get 5/7 minus, we sub in the 0, we get 0. So our final answer here is 5 pi over 7. Number 32, find the volume of the solid of revolution formed by rotating the region bounded by the x-axis and the graph of y equals x cubed from x equals 1 to x equals 2 about the x-axis. So again, we start by sketching the graph. And we've got y equals x cubed. I'm going to stretch this out a little bit just to make it kind of easier to see what we're doing. From x equals 1 to x equals 2. So let's just say 1 is here and 2 is here. So there's our region, and we want to rotate this about the x-axis. So I'm going to draw my reference rectangle in my shaded region. So here's my shaded region. And since this is a vertical rectangle, this is a dx problem. So setting up my integral, it's dx. And then my limits are x values. So we're going from x equals 1 to x equals 2. And our volume will be pi times the radius squared. So the radius is just the vertical length or height of this reference rectangle. We want top minus bottom, and this top equation here is y equals x cubed. The bottom equation down here is just y equals 0. So top minus bottom is x cubed minus 0, or just x cubed. So we are integrating x to the power 6 times dx from 1 to 2. We can do that by hand using the power rule. We get x to the 7th over 7 from 1 to 2, and let's not forget the pi, that's important. And then we sub in the 2, So 2 to the power 7 over 7 minus, and we sub in our 1 to the power 7 over 7. Okay, 2 to the power 5 is 32. And then 64, 128 minus 1 over 7 gives me 127 over 7 times pi. 33. Find the volume of the solid of revolution formed by rotating the region bounded by the x-axis and the graph of y equals x squared times the square root of 2 minus cosine x to the fifth from x equals 0 to x equals 2 about the x-axis. So again, we start with a graph. And I'm just going to do my best here. Our graph is doing something kind of crazy like so. And we'll call that 2. We've got 0 over here. We're rotating about the x-axis, and our function is y equals x squared times the square root of 2 minus cosine x to the fifth. So our setup, let's do our reference rectangle here. And then here's my shaded region. So I'm integrating all the way from x equals 0 to x equals 2. This is a dx problem. So we want pi times our radius squared times dx. And our radius, in this case, the height of the rectangle, top minus bottom, x squared times square root 2 minus cosine x to the fifth. So all of that squared times dx. And then this is labeled as a calculator problem. It is doable by hand using a u substitution. So let's see how that would work just for the fun of it. We can let u equal, well, first of all, we can simplify this a little bit because we've got all this stuff squared. So pi times the integral from 0 to 2. The x squared squared is x to the fourth. And then the square root of 2 minus cosine x to the fifth squared is just 2 minus cosine of x to the fifth times dx. So we can let u equal x to the fifth, and then du equals 5x squared, 5x to the fourth dx. And I've got x to the fourth dx in my problem already. So here if I divide by 5, 1/5 du equals x to the fourth dx, and then I can rewrite my integral. I can't use 0 and 2 because those are x values. I would need u values, or just leave the bounds blank. So x to the fourth dx becomes 1/5, so bring out my 1/5, du, and then 2 minus the cosine of u. And if we want to convert our bounds, let's see, when x equals 0, I'm going back to this equation right here. When x equals 0, u equals 0. That was easy. And then at x equals 2, u equals 2 to the power 5, or 32. So in terms of u, we're integrating from 0 to 32. Pi over 5 is a constant multiple, so that stays. And then we integrate 2, we get 2u. And we integrate minus cosine u, we get minus sine u from 0 to 32. So pi over 5 times 2 times 32 is 64 minus the sine of 32. Minus, and then when I put 0 in for u, I just get 0. So this would be my final answer. If I needed an exact answer, pi over 5 times 64 minus sine 32. Or if we convert that to a decimal, it's approximately 39.866. Find the volume of the solid of revolution formed by rotating the region bounded by the x-axis and the graph of x equals y cubed from y equals 0 to y equals 1 about the y-axis. X equals y cubed. So the graph of x equals y cubed looks like this approximately in quadrant 1. And we'll say a value of y equals 1 is about right there. And we're rotating now around the y-axis. So this is x equals y cubed. This time we want to draw a horizontal rectangle. So this will be a dy problem. And here's our shaded region going from y equals 1 up to y equals 0. So this is a dy problem. Our volume is going to be pi times our radius squared. Our y values go from 0 to 1. And then the the horizontal length of that reference rectangle, we're going to do right minus left. So y cubed minus 0, or just y cubed. Okay, so our integral becomes pi times integral from 0 to 1 of y to the power 6 dy. So pi, and now we use power rule, y to the 7 over 7, I'm going to bring the over 7 out, from 0 to 1. We sub in 1, we just get 1. We sub in 0, we get 0. So the answer is just pi over 7. 35. Find the volume of the solid of revolution formed by rotating the region bounded by the y-axis and the graph of y equals 7th root of x to the 5th from y equals 0 to y equals 1 about the y-axis. So we're going about the y-axis, the 7th root of x to the power 5. So that's going to look something like that. And we've got 1 right about there. We're going to use a horizontal rectangle, so this is now a dy problem. Here's my shaded region here. And this is the graph of y equals x to the power 5 over 7. But since this is a dy problem, I need to solve my equation for x. And I'm going to do that by raising both sides to the power 7 over 5. So x equals y to the power 7 over 5. And since it's a dy problem, I'm not going to need this other version of the equation. So we'll take that out. We'll just use our equation for x in terms of y. In a dy problem, we want everything to be in terms of y. So our volume is pi times the integral from y equals 0 to y equals 1 of, now my horizontal length of my rectangle, we'll do right minus left, so y to the power 7 over 5 minus 0 squared times dy. So that's pi times the integral from 0 to 1 of y to the power 14 over 5. When you have a power raised to a power, you multiply your exponents, dy. And then we can use power rule here. So we get y to the, I need to add 1 to 14 over 5. So I'm adding 5 over 5. Let's get 19 over 5 and then divide by 19 over 5, which is the same as multiplying by 5 over 19. And we evaluate that from 0 to 1. When y is 1, I just get 5 over 19. When y is 0, I get 0. So final answer, 5 pi over 19. 36, let R be the region bounded by the graphs of y equals ln x and the line y equals x minus 2. So the pink one is our linear function, y equals x minus 2. And then the yellow one is our log function, y equals ln x. Part A, find the coordinates of the points at which the two graphs intersect, then find the area of R. So we will graph these on our calculator and get the points of intersection. This first point of intersection, 0.1586, comma, negative 1.8414. We probably don't need to be quite that precise. 3.1462, comma, 1.1462 for this other point of intersection here. Now we want to find the area of this region. So we could do this either as a dx problem or a dy problem. Since our equations are both written as y equals something in terms of x, it'll be a little easier if we do a dx problem. So I've got a vertical rectangle. This is my region R here. And for area, we just need to integrate from, since this is a dx problem, I need to use x coordinates. So from 0.1586 to 3.1462, top minus bottom. So ln x minus x minus 2 times dx. And we can integrate this using Math 9 on our calculator. We should get 1.949. Part B, write and evaluate an integral to find the volume, so we want volume, of the solid generated when R is rotated about the horizontal line y equals negative 3. So I don't have a whole lot of room here. I'm just going to put y equals negative 3 right here, even though that's obviously not to scale, because our point of intersection down here has a y coordinate of negative 1.8-ish. But we're going to call this y equals negative 3, and we are rotating about this line. So I'm going to, for this one, I'm going to use the washer method. We're going to have an outer radius and an inner radius. So my outer radius is here. This is a dx problem. And then my inner radius, we'll do that one in a different color right here. Okay, so volume equals pi. This is a dx problem, so I need to use my x coordinates. We're going from 0.1586 to 3.1462. And we're going to do the outer radius squared. So the outer radius, top minus bottom, is ln x minus negative 3 squared minus, and then our inner radius squared. Our inner radius, we're going to do top minus bottom, so x minus 2 minus negative 3, and square that. And all of that times dx. And if we evaluate that on our graphing calculator using Math 9, we should be getting 34.199. Part C, write and evaluate an integral to find the volume of the solid generated when R is rotated about the y-axis. So if we're rotating around the y-axis and we're using washer method, we have to draw a rectangle perpendicular to our axis of rotation. So we have an outer radius here and an inner radius here. Now this is a dy problem. When it's a dy problem, we need to solve our equations for x. So instead of our linear function being y equals x minus 2, we solve that for x, we get x equals y plus 2. And then for our log function, instead of y equals ln x, we get x equals e to the power y. And our volume equation becomes v equals pi times the integral. This is a dy problem, so we're going to use y values here. We go from negative 1.8414 to y equals 1.1462. Our outer radius squared, we're going to do right minus left. So y plus 2 minus 0 squared minus, and then inner radius squared. Inner radius, do right minus left, is e to the y minus 0 squared times dy. And that should give us 5.443. 37. Let f and g be the functions given by f of x equals 1/4 plus sine pi x and g of x equals 4 to the negative x. Let R be the region in the first quadrant enclosed by the y-axis and the graphs of f and g, and let S be the region in the first quadrant enclosed by the graphs of f and g as pictured below. Part A, let's find the points of intersection for f and g. So we can graph these on the calculator and get points of intersection. I'm going to label on the left this point of intersection as A, and then on the right this point of intersection as B. So we get point A has coordinates 0.1782, comma 0.7811. And then point B has coordinates 1, comma 1/4, or 0.25. Part B, write and evaluate an integral to find the area of the region bounded by the graphs of f, g, and the x-axis. So we want the area bounded by f and g and the x-axis. I'm going to go ahead and shade that. We've got this little piece over here to the left of the y-axis, and then we have this region in here all the way over past this point of intersection to include that little piece right there. Now here we just want area. So we need to find a few other values. We need the x-intercept over here on the left, and we need the x-intercept over here on the right. Okay, so let's call this one point C. And point C has coordinates negative 0.080, comma 0. And then the one on the other side over here we'll call D. And D has coordinates 1.080, comma 0. So the area will be the integral from, and now we're not going to be able to do this all in one go. We've got the area under the yellow curve between C and A. And I'm just going to write from C to A here. And it's the x coordinates. So let's write x equals C and x equals A. So we know we're entering the x coordinates from point C and the x coordinates from point A. So we're going to integrate from C to A. So we're splitting this up into one region right here. And then we need to stop or start a new integral after that point. So we're integrating the yellow function, and that is the y equals 1/4 plus sine of pi x. So let's call that y1. So integrating y1. And then this other function is our y equals 4 to the negative x. And we'll call that y2. So y1 times dx, this is just area, plus the integral. Now we're going to go from a to b. We need to stop our integral here at b. So we're integrating from x, the x coordinate of a, to the x coordinate of b. And we want to integrate y2 with respect to x, plus, and then we're going to integrate from b to d. X equals b to x equals d, and we're integrating our top function y1, which gives 0.496. Part C, write and evaluate an integral to find the volume of the solid generated when r is revolved about the horizontal line y equals 8. So I don't have a lot of room to work on this graph, so I'm just going to redraw the graph over here and zoom in around region R. So we've got our y-axis, our x-axis down here, region R. You know what, I'm drawing it exactly the same. That's no good. Region R, let's put like here. And then y equals 8. This is not to scale, but y equals 8 is up here. So we've got here our point of intersection at A, and then this is at x coordinates of 0. So we do want to draw our rectangle perpendicular to our axis of rotation. So we have this outer rectangle or outer radius here. So this is a dx problem. And then we have an inner radius here. And our setup for volume, it's going to be pi. We're doing disk method. Nope, we're doing washer method. It's going to be pi times the integral. This is a dx problem, so we're going to use the x coordinates. We're going from x equals 0 to x equals the x value at point A, so 0.1782. And then we're integrating outer function, or outer radius squared. So the outer radius, we'll do top minus bottom, is 8 minus, and I don't have this labeled now, but this is my f of x here. So top minus bottom is going to be 8 minus f of x, which I have in y1. That's outer radius squared minus, and then for my inner radius, I want top minus bottom. So 8 minus, and then this other function here, which is g of x, or the equation in y2. So we need to square that. And that's multiplied by dx. And that is giving me 2.979. Part D, write and evaluate an integral to find the volume of the solid generated when S is revolved about the horizontal line y equals -1. Okay, so we're going to have y equals -1 down here, y equals -1, and now this is our axis of revolution. So we have an outer radius. Let me go ahead and shade the region in question. So we're working to find the volume when we rotate S around y equals -1. So we have an outer radius, and remember your radius always has to touch your axis of revolution. So outer radius is all the way up there. And then our inner radius here. So this is a dx problem. And we've got volume equals pi times, since it's dx, we're going to use x coordinates. We're going from the x coordinate of point A, 0.1782, to the x coordinate of point B, which is just 1. Then we need the outer radius squared, so top minus bottom, and the top function here is f of x. So f of x minus -1, which becomes f of x plus 1, and we square that outer radius. Minus, now our inner radius, top minus bottom, will be g of x minus -1, or g of x plus 1, and then we square that times dx. And there we get 4.559. Find the volume of the solid resulting from rotating the region enclosed by y equals x squared and y equals x cubed about the vertical line x equals 1. Okay, so we've got an intersection point here at 1, and we're rotating around the line x equals 1. And if we're going to do washer method, we have to draw our rectangle perpendicular to our axis of rotation. So my outer radius will be here and my inner radius here. So this is a dy problem, and in a dy problem we want to solve our equations for x. So the top function is the y equals x squared, and that means x equals square root of y. And then our bottom function, y equals x cubed, becomes x equals cube root y. So here's our shaded region that we're going to rotate around y equals 1. And our setup will be volume equals pi times the integral. This is dy, so we need y coordinates. We're going from, this is the point 0, 0 here, and this is the point 1, 1 here. So we're going from y equals 0 to y equals 1. My outer radius squared. So outer radius, I'm doing right minus left, so 1 minus square root y squared minus, and then inner radius, right minus left, 1 minus cube root y squared. All of that times dy. And that is 0.209. Okay, so there's our y equals sine x. And then here's y equals 1. Oh, I missed it a little bit. Let's say right there. So here's where sine equals 1. And then we've got y equals x squared, which comes in kind of like that. Okay, so key points here, we're going to need to get that point of intersection. We know this one is 0, 0. And we have this function here is y equals x squared. And then this function is y equals sine x. We're rotating around this horizontal line, which means we need a vertical rectangle. So we've got outer radius and inner radius. And our volume. So this is the shaded region here that we're rotating. So volume equals pi. This is a dx problem, so we're using x coordinates. We're going from x equals 0 to x equals the x coordinate at this other point of intersection, which is 0.8767. So that's that value right there. And we're going to do the outer radius squared, top minus bottom. So this is y equals 1. Top minus bottom is 1 minus x squared. That's the outer radius. We want to square that. Minus, and then our inner radius, top minus bottom, 1 minus sine x squared. All of that times dx, which is 0.573. Number 40, find the volume of the solid resulting from rotating the region enclosed by y equals x squared and y equals x cubed about the vertical line x equals -1. This is my least favorite graph to draw. It's very difficult to draw x squared and x cubed. So I usually end up making it a little bit distorted just so I have some space to draw in. So we'll call that x squared, and then x cubed kind of comes in from below there, and they intersect here at 1 and up here at 1. So we're asked to draw, we have to rotate around x equals -1. So yeah, I didn't leave myself enough room. We'll just say, okay, this is not going to be to scale, and put x equals -1 over here. Okay, so if we're going to use washer method, then we need a horizontal rectangle. Outer radius will look like that, dy, and then we have our inner radius here, which doesn't look very different the way I drew it, but they're touching different things. And then this is the area of our shaded region here. Okay, so our volume, we're using washer method. Pi, we're integrating with respect to y. So we're going from y equals 0 up to y equals 1. We want outer radius squared minus inner radius squared. Okay, so let's label our equations. In a dy problem, we have to solve these things for x. Well, this bottom function is x cubed, so x equals cube root y. And then this top function is y equals x squared, so x equals square root y. So outer radius, right minus left, is going to be cube root y minus negative 1, or cube root y plus 1 squared, minus, and then our inner radius, square root y minus negative 1, or square root y plus 1 squared, and all of that times dy, which equals 0.838. And finally, we have number 41. Find the volume of the solid resulting from rotating the region enclosed by y equals sine x and y equals x squared about the horizontal line y equals negative 1. Okay, so here we go again. Y equals sine x, something like that. Y equals x squared, something like that. And we're rotating about the horizontal line y equals negative 1, which is down here. Yeah, down here. So we're rotating around y equals negative 1. Now we want to draw our rectangles perpendicular to our axis of rotation. So we have this really long outer radius, and then not quite so long, but still long inner radius. And since these are vertical rectangles, this is a dx problem. Okay, so we want our equations in the form of y equals sine x is the top function, and y equals x squared is our bottom function. Points of intersection, we've got 0, 0. And then we have our other point of intersection over here that has an x coordinate of 0.8767. And this is our shaded region here. So volume equals pi, this is dx, so we're going from x equals 0 to x equals 0.8767. Outer radius squared, top minus bottom, so sine x minus negative 1. We're going to square that, minus, and then our inner radius is x squared minus negative 1. We're going to square that, and then multiply all of that by dx, which gives 1.132.